This video we will describe Kepler's 3 laws of planetary or orbital motion. So the 3 laws are as follows. The first is called the Law of Ellipses. The path of the planets about the Sun is elliptical in shape, with the center of the Sun being located at one focus, or one of the foci. An imaginary line, second one, imaginary line drawing from the center of the Sun to the center of the planet will sweep out equal areas in equal intervals of time, which is called the Law of Equal Areas. Then the third law, the ratio of the squares of the periods of any 2 planets is equal to the ratio of the cubes of their average distances from the Sun, and this is called the Law of Harmonies. The Law of Ellipses is pretty simple. If we want to draw an ellipse, we would just take 2 thumbtacks, and they would be the foci of an ellipse, and each ellipse has 2 foci. And then we would just take a string, and we would just draw a circle using that loop of string. And that would show us what an ellipse is. Okay, but that explains the planets, and that's something we'll try to do in lab. The law of equal areas is the second law. It's the law of equal areas. It describes the speed at which any given planet will move while orbiting the Sun. The speed at which any planet moves through space is constantly changing. A planet moves fastest when it is closest to the Sun and slowest when it is furthest from the Sun. Yet, if an imaginary line were drawing from the center of the planet to the center of the Sun, the line would sweep out the same area in equal periods of time. So what they're saying is this area is equal to this area, which is equal to this area. So our equal time periods, okay, show us that here we're covering more distance in this time period, which means it's going faster when it's closest to the Sun. And then here we're going a small distance in the same amount of time, which means it's going slower. So that's what the law of equal areas tells us. These areas are all equal, which means our speeds are going to vary in the elliptical orbit. And then the law of harmonies. It compares the orbital period and radius of the orbit of like planets. So essentially, it's the time period squared is equal to 4 pi squared over g, which is the gravitational constant, m, the mass, okay, of the Sun, and then times a, astronomical units, cubed. And this is what you see, and I'll give an example of how to use this equation and what it all means. But then we just assume that for this, 4 pi squared over g, okay, is all equal to 1, which will be beneficial. That's why we use this as mainly the equation. So, in review from the last video, a satellite is a projectile which falls around the Earth instead of into it. So at A and B we're hitting the Earth, but at C and D we are orbiting. On the Earth's surface, for every 8,000 meters along the horizon, we get a downward curvature of about 5 meters. We know if we had a circular orbit that the satellite's velocity would go off at a tangent, and that the force of gravity and the acceleration vectors would go towards the center, which in this case, if this is a satellite around the Earth, the center would be the Earth. Now, this centripetal force that keeps a satellite in action, because our satellite wants to go off at a tangent, but there's an inward force pulling it back in, and that force, of course, is gravity. So our centripetal force in this is gravity. Now, with an elliptical orbit, it's very similar, except we're not at right angles, okay? Now, at this point, we're at a right angle with our velocity and force vectors, but here we're not. And here we're not, and then here we're at. So if we're on the flat line here, we're at a right angle. But otherwise, it's our net force vectors are always going to go towards the center of the Earth. So it's not always going to be at 90 degrees, like what we saw with circular orbit. Orbital speed equation. If I want to find how fast something's orbiting, I just take the square root of 6.67 times 10 to the 11, or universal gravitational constant, times the mass of the central item. So it could be the mass of the Earth. It could be the mass of the Sun, depending if we're talking about our solar system. But it's the mass of the central divided by the distance between them. That's where the R comes in. The acceleration, very similar, except we're not square rooting. So it's just going to be the constant times the mass of the center divided by the distance between them squared. But that will help us find speed and acceleration. The orbital period equation is right here. T squared over R squared equals 4 pi squared over G times the mass of the central atom. and we can use that to solve some different problems if we encounter them, okay? But here's the big thing. None of them has the mass of the orbiting body. So like we have the Earth and the moon's orbiting. The mass of the moon, not important. The period, speed, and acceleration of the satellite are only dependent upon the radius of the orbit and the mass of the central body, not that the satellite counts. So the moon going around the Earth, the mass of the moon is irrelevant. The mass of the Earth is what counts. So that's what we have to remember. The mass of the satellite, not important. So here's an example. We got a satellite that wants to orbit the Earth at a height of 100 kilometers above the surface of the Earth. We want to find the speed, acceleration, and orbital period of the satellite, given the mass of the Earth is 5.98 times 10 to the 24th, and the radius of the Earth as 6.37 times 10 to the 6th. Now, we want to use the velocity equation, so we're taking the square root of our number. And first we take the universal gravitation constant, and we multiply it by the mass of the Earth. Then we divide by the distance. Now, the distance is from the center of the Earth to the satellite, which means we got to take the radius of the Earth, and then we have to add to that this 100 kilometers all above the surface of the Earth that the satellite is located. So this number down here is radius plus 100, so it's 6.47 times 10 to the 8th. Put that on my calculator, take the square root, and I get an orbital velocity of 7.85 times 10 to the 3rd meters per second. The acceleration, same numbers, except no square root, and we just square the distance. So we get an acceleration of 9.53 meters per second squared. And then when we want to find the time period, so we got t squared, we take our radius and we cube it, 4 pi squared. G is here, mass of the Earth is here, and we just use we could cross multiply, solve for t, but you get t to be 5,176 seconds, or 1.44 hours for that to happen. Okay, here's another problem. The period of the moon is 27.2 days. Converted to seconds, it's 2.35 times 10 to the 6 seconds. We want to find the radius of the moon's orbit and the orbital speed of the moon. Okay, mass of the Earth, radius of the Earth, same as before. If we want to find the radius, we're solving for r. So we take our time, 2.35 times 10 to the 6th, and I didn't square it here, but we squared it. We got 4 pi squared. We have the universal gravitation constant, and we have the mass of the Earth. Cross multiply, solve for r, take the cubed root, and we get 3.82 times 10 to the 8th meters, which is the radius of the moon's orbit, which is kind of interesting, right? I mean, we can solve that pretty simple, and it fits as long as we know time period. If we want to find that velocity, remember, square root of universal gravitational constant times the mass of the central, which is in this case the Earth, divided by the radius, which is what we just solved for previously. And we find the orbital velocity of the moon to be 1.02 times 10 to the 3rd meters per second. Lastly, we got a satellite that orbits the Earth of an orbital period of 24 hours, thus matching the period of the Earth's rotational motion. A special class of satellites is a geostationary satellite. A geostationary satellite orbits the Earth in 24 hours along an orbital path that is parallel to an imaginary plane drawn through the Earth's equator. Such a satellite appears permanently fixed above the same location on the Earth. So if you're standing there, you'd see it the same place all the time. A geostationary satellite wishes to orbit the Earth in 24 hours, which is 86,400 seconds. How high above the Earth's surface must it be located? Again, mass of the Earth, radius of the Earth are known. So we want to find the radius of our orbit. We square our time, 4 pi squared, constant, mass, punch the numbers in, take the cubed root, and we get 4.23 times 10 to the 7th meter. So that's how far away it must be. But before we're done, we have to think about above the surface. So to get it above the surface, we have to subtract the radius of the Earth, and that's how far above the surface, 3.59 times 10 to the 7th. Remember, this number is from center to center. So when you solve, be very careful. I mean, you'll get dinged on mastery if you don't remember the radius of the Earth to subtract it if we're talking about the surface, like you see here. So weightlessness. is simply a sensation experienced by an individual when there are no objects touching one's body and exerting a push or pull upon it. So it has no touch. So it's essentially just when gravity's on you. So when all contact forces are removed. When in free fall, the only force acting upon your body is the force of gravity. And since the force of gravity cannot be felt without any other opposing forces, you would have no sensation of it. You would feel weightless when in a state of free fall. They're common on the roller coasters and things we talked about last week. Sometimes when you go over a hill too fast in your car and you feel yourself rise above the seat, that also is weightlessness. G's are normal rate. Since the chair is unstable, flying at the same rate as you is unable to push upon you. Normal forces only result from contact. So to have a normal force, we got to have contact. So to experience weightlessness, you would weigh as much as you always do. So that does not mean you lose weight. It just means you don't have any sensation of this weight because you're not making contact with anything. You're not getting the normal force. So it's only a sensation. Doesn't mean you lost weight. Again, you can pause and read this if you like. But a person in free fall does not experience any contact force and thus feels weightless. So if you're on a chair and dropping only, you would not feel any contact force. A scale does not measure your weight. Because you're standing on it, it measures the upward force applied to your body. A scale reads normal force. Using that information, if you're on an elevator going at a constant speed, which means no acceleration, gravity and normal force would be equal, so your weight would be accurate on the scale. If you're upward accelerating, normal force will be greater than your actual weight, so your weight would read greater on the scale. If you're going with a downward acceleration, force of gravity, your weight would actually be greater than what the scale would read, so your scale would read less than that. And then, of course, if you're accelerating at 9.8 meters per second, you're not even touching the scale anymore because there is no more normal force. So even though the force of gravity is there, your normal force would be 0. So you would have no weight, and that's that feeling of weightlessness that you feel. Weightlessness in orbit. Astronauts are weightless for the same reasons that riders in a free-fall amusement park ride or a free-falling elevator are weightless. They're weightless because there's no contact force pushing or pulling their body. So all they have is gravity acting on them. I'm trying to find the one thing to talk about here. Here we go. In fact, if it were not for the force of gravity, the astronauts would not be orbiting in circular motion. It is the force of gravity that supplies the centripetal force, this inward acceleration that's characteristic of circular motion. The force of gravity is the only force acting upon their body. The astronauts are in free fall, like the falling amusement park rider and the falling elevator rider. The astronauts and their surroundings are falling towards the Earth under the sole influence of gravity. The astronauts and all their surroundings, the space station with its contents, are falling towards the Earth without colliding into it. Their tangential velocity allows them to remain in orbital motion while the force of gravity pulls them inward. Again, they want to go this way, but the Earth pulls them back in. So circular satellite motion, again, at right angles, everything's nice and neat. At elliptical satellite motion, the force always goes towards the center of the body, but the velocity is still tangential. Thinking about energy, since this distance is always constant, right? Our potential and kinetic energies always stay the same because our velocity is pretty constant throughout. We're not changing our velocities. Therefore, potential and kinetic energy is constant throughout circular motion. But if we're in elliptical orbit, like is what we see, okay, in our solar system, if you look at A, our distance is short, and the law of equal areas tells us this, we're going to travel faster, which means our kinetic energy is high, potential energy is low. As we get to B, kinetic energy decreases and converts to potential. As we get to C, our kinetic energy is really short because we're not traveling as fast, and our potential energy is great. D, it starts to come back a little bit with the kinetic energy. E, it starts to travel a little faster, but at A, we're going the fastest. At C, we're going the slowest. And that's applying the second law of Kepler's laws. So there's energy. When you look at the sample problems, don't forget the radius of the Earth.